replicator equation, which is like a dynamical system that is used a lot in evolutionary game theory. And then I'm going to show you that the replicator equation is the cousin of the generalized linear Lotka-Volterra, and as such, we can connect these two things. And in fact, that's how we can solve a few problems in Lotka-Volterra, like we did yesterday. We didn't want to integrate dynamics. And we turned this into a game, solved the game, turned back into Lotka-Volterra. Right? So this basically builds like another part of your toolbox for analyzing this type of models that I think is quite interesting. And it's a very deep connection that has some surprising twists. So I'm not sure I fully really like exploited this connection as much. Anyway, game theory. So game theory is about the same date as Lotka-Volterra, right? Like the first paper formally in game theory was von Neumann on the theory of games of strategy that was published in 1928, so 2 years after the paper by Volterra. And then this took off really in applications to economics. And this was due to like a book with Morgenstern that was published in 1944. Right? And this really put game theory squarely within economics. And even today, a lot of the theoreticians in economics, they work on some aspects of game theory. And then maybe you've seen the movie A Beautiful Mind, John Nash, 1950, in this paper that is basically a third of a page in PNAS. It said, blah, blah, blah. This becomes the Brouwer's fixed point theorem, done. Became super famous for this idea of Nash Equilibria, right? You should read the paper because it will only take you like less than a minute to read the paper. This was a very important contribution because he introduced this idea of Nash Equilibrium. And then this took off, and mathematicians and economists started studying game theory. Where does biology come in? It comes in with the work of John Maynard Smith in 1982 that wrote this very interesting book that is called Evolution and the Theory of Games, where he showed that the very same concepts that we would use in game theory could be applied to study evolution of natural population and behavior and things like that. And he also introduced an interesting concept, which is like an extension, if you will, of Nash equilibrium, that is this idea of evolutionary stable strategies. So there is this equilibrium, but can I access this equilibrium by evolution or not? And then this launched this idea of evolutionary game theory, in which basically we will see like the strategies are the populations themselves or the phenotypes themselves. And to study this, one of the most useful like, tools is what is called the replicator equation that was introduced in 1978 and was studied a lot by Hofbauer and Sigmund that I already cited several times, and now I cite them again because they really are the masters of this thing. Okay, so we're going to get to this point of introducing the replicator equation. How does it connect to Nash equilibria and evolutionary stable strategies? And then we're going to connect it back to what we've been doing like on Lotka-Volterra. So I'm not going to do all of game theory, of course. I'm just going to mention the facts that I need to go on. So what I want to do is like 2 players matrix games. So 2 player means what? There's 2 players. In matrix games, what does it mean? Is that each player has a set of strategies. You can think of like the simplest game like rock, paper, scissor, right? So you have 3 strategies, 2 players, and then we play. Right? So more formally, we have like each player has a set of strategies that are pure strategies that they can choose from, rock, paper, or scissors. So that would be the set big S1. And so player 1 chooses one of these strategies, out of this set. So imagine that player 1 chooses like little s I out of big S of player 1, right? So this is like the strategy chosen by player I, right? And similarly, the second player chooses a strategy. And very importantly for the development of this thing, each player does not know what the other player is going to play, because otherwise it's a much different problem, right? So it's exactly like rock, paper, scissors. That's why we have to coordinate and play at the same time, because otherwise if I know what you played, I have an obvious choice to beat you, okay? And then when we have like these 2 players that have chosen, like player 1 has chosen a strategy S1, and player 2 has chosen a strategy S2, what we can do is to define a function that we call the payoff, and is defined for each player, right? So this, for example, the payoff of player 1 when player 1 plays S1 and player 2 plays S2, it's like the number of points or the number of dollars that you win or something like that, right? So we call this the payoff. Because we have like discrete strategies and only 2 players, it makes a lot of sense to organize these payoffs in a matrix, right? And this we call the payoff matrix because we have no fantasy whatsoever. And so like we call A the payoff matrix of player 1, and then we will call B the payoff matrix of player B. Right, so this would be, imagine a matrix that I have my player 1 choosing S1, S2, and S3. So this is like what player 1 chooses. And then player 2 chooses S1, S2, S3, and S4 because they don't need to have exactly the same number of strategies, for example. And here I put like basically a payoff of 1, S1, S1, right? And then like that. Okay, so is this clear? Like we just organize it in this matrix. And just to give you a simple example that you've seen over and over and over again, we can write these matrices for the famous prisoner's dilemma. So you know like the story. There's like 2 people that are allegedly committed a crime, but the police does not have enough evidence to charge them. And so they put them in separate cells, and they go to each one of them, and they offer them a deal. And the deal is, if you confess, you know, like, and you allow us to put the other person in jail, you can go for free, right? What the police is not saying, because it's not to their advantage, is that they don't really have enough to charge them for the crime. So if both of them refuse to confess and rat on the other person, they will be maybe sentenced to some minor misdemeanor or something like that, such that they would have an advantage, right? So more formally, like each player, there's 2 players, there's 2 strategies. So this is my matrix for player 1. The player 1 can decide to cooperate, meaning stay silent. So it cooperates with the other player, or defect, meaning confess to the crime and have, like, send the other player to jail. And similarly, the player 2 can do the same thing, right? Confess, cooperate, or defect. And so like the payoff has to have some sort of structure. For example, imagine that if both of them stay silent, they get sentenced to 2 years, right, for some other minor crime that they have like proofs for. But then, if player 1 decides to rat on the other person, right, so he defects, and the other person does not confess, player 1 is let free. So he gets 0 years in jail, which is good. Right? On the other hand, if this player stays silent and the other player rats on him, he gets sentenced to 5 years in jail. Right? And if both of them confess, then they got both sentenced to a certain number of years. Right? So if you have any matrix with this sort of structure of payoffs where which one is greater or lower, you have the prisoner's dilemma. It doesn't need to be all negative, or it doesn't need to be like this. And one good fact about the prisoner's dilemma is that the matrix for player 2 is exactly the same. But now this is what player 2 plays, well, here is what player 1 plays, and similarly the columns here are player 2 and here are player 1. So when we have this type of thing where matrix A and B are identical, we call a symmetric game. Okay, so both of them have the same type of payoffs. Okay, so this also allows us to introduce this notion of a Nash equilibrium. And the way we're going to do this is to say, let's think that we're player 1, right, the first prisoner. And then we can look at our options, thinking, what is the other person doing? And then we can choose what we should do. Right? So imagine that, for a moment, that player 2, we think it will be stay silent, right? At that point, what should I do? Should I confess, right, and get sentenced, cooperate and get sentenced to 2 years, or I should rat on him and you know, defect? At that point, I'm let free from a very individualistic slash ungenerous perspective, I should write on the other people, right? So I should choose defect. Now, what if player 2 defects on me? Well, then, if I stay silent, I get sentenced 5 years. And if I defect, I get sentenced to 4 years. Again, I should defect at this point, right? It's convenient for me. So because it's convenient for me to defect, no matter what the other person is doing, I will defect. But then by symmetry, the other person is going to defect, right? And so the system will get stuck where? Where both of them are going to defect and hence get sentenced to 4 years in prison, which is not the ideal outcome if you think, right? But no one has an advantage at changing their own strategy without the other person changing their own strategy. And when this happens, so that there's no advantage to a player to change their strategy without something else moving, we call that a Nash equilibrium. Okay? Is this clear enough? Notice that if they could trust each other, or if they could somehow decide to cooperate, then they could reach a much better payoff, for example, -2, -2. Right? But this would require trust and communication. And this model, in fact, in evolution is used as a typical model to test the evolution of cooperation, right? Because you can imagine that this is one bout of the game, but what if I were to repeat this game over and over and over again? Is there a way to introduce some rules to get better payoffs? This is mathematically very challenging to do. And one fun fact that I don't know if you know, so in the 1980s, I think, there was this professor of sociology in Michigan, or maybe political science. Anyway, this is Axelrod. And so he decided to do this thing. Because this is difficult to treat mathematically, he decided to hold a competition. Right? So you could write your own program that would play the prisoner's dilemma against other programs over and over again for an unspecified, and that's very important, number of bouts. And then you could submit your program, and you didn't know which other programs were there, so you could not fine-tune it very much. And then they would just compete all the programs against each other and see who would win, meaning who gets sentenced to the less number of years in prison over all the bouts. And actually, there, Rappaport, that was back then at the University of Chicago in the Committee of Mathematical Biology, wrote this very short program that has a very simple strategy that is called tit for tat. And tit for tat does what? When I meet with a new player, I cooperate, right? So I start nice. And then I do whatever the player did the previous turn, right? So if you cooperate with me the first turn, then I'm going to cooperate again. But if you defect on me, I will defect, right? And so this tit for tat, which is start nice and then follow whatever the other person did the previous turn, turned out to be the winner. And it was one of the simplest programs that were submitted. And what is even more amusing, so there was this little report, so then the next year they hold the competition again, and now everybody knows that tit for tat has won. And so people submit their program, and who wins the second year? Tit for tat, which tells you that academia is not that good. All right, so just to say that this is actually a model that even though it's very simple, it actually plays a very special role in evolutionary biology. Now, in this game, what we're doing is we're asking people just to choose one strategy. But especially when we're thinking of these repeated games, but also in general, what we could introduce is the idea of a mixed strategy, right? So instead of selecting one of these things, you have a set and you have to choose one, you just have to have a probability distribution over the set, right? So imagine that I want to play cooperate with a certain probability, 72%, and defect with probability 28%. And every time I play this game, I just draw a random number and then I choose. Okay, this is what we would call a mixed strategy. More formally, we have some sort of vector that we typically call x over the strategies, right? So this is between I is equal to 1 to the size of my strategy set, such that this sum is 1, and these are all non-negative. Thank you very much. So these are basically proportions or probabilities, right? And then we need to have something that looks like the payoff for these mixed strategies, right? So instead of just looking at one number in this table, we need to do some sort of average, right? Because we have to compute what is the probability that I get this payoff or not. And of course, the most natural choice for that, for example, for the payoff of player 1, would be a weighted sum, right? Where we have like over all this is like I in, for example, let's say for I equals to 1 to the size of the strategies of player 1, and then say j between 1 and the set of strategies of player 2, and then we call x for player 1, and we have a similar thing for player 2 that we call y. Then we could say this is the probability that player 1 plays strategy I. This is the payoff that they would get if they were to play strategy I and say I and j, and then y of j, right? So this would be the probability that I play something.
In the slide you have 1 and 2 there.
Oh yeah, it's a typo, sorry. But so this is the probability that player 1 plays I, player 2 plays j, and this is the payoff that player 1 would get. So you can see this is some sort of an average. And if we write this in matrix form, which is the way I prefer, what would we have? We would have like this, you can see it's like a sum. These would be the rows, this would be the columns. So we would get basically the same thing. Here we could write it as x transpose a y, right? So this would be exactly this weighted average. And then for player 2, we would get y transpose bx. Okay? So this is just like a more compact notation for the same thing. Now we have to get like to a few inequalities just to define this idea of Nash equilibrium. And so the first thing we're going to say is, are there mixed strategies that are better than other mixed strategies? Always, right? So is there some sort of idea that this is definitely better than the other strategy? So what we can introduce is this idea of a strategy being dominated by another strategy. So for example, we can say a mixed strategy X is dominated by, say, X tilde, when if we have that X tilde transposed AY, so the payoff when I play X tilde and the player 2 plays Y, is greater or equal than X transpose AY for all Y in the simplex, right? So this means that no matter what the other player is playing, I'm better off playing X tilde than I'm playing X. Okay, you can rewrite this, like, and that makes it a little more explicit. Like you could rewrite this as X tilde minus X transposed AY is greater or equal than 0 for all Y, right? It's the same thing. Okay, so you have an advantage at playing X tilde. Now, with this notion, with this kind of inequality in mind, we can define Nash equilibrium for mixed strategy games. And so, like, this is like Nash equilibrium. And so what we have is that we have a pair of mixed strategies, X, Y, tildes, is called the Nash equilibrium for a two-person matrix game if X tilde transposed A, Y transposed is greater or equal than X transposed A, Y tilde for all X. And just to translate this into English, what does it do? Like it says, when I play X tilde and the other player is playing Y tilde, I'm better off playing X tilde than any other X. And similarly, we have the symmetric condition, right? The saying Y tilde B X tilde is greater or equal than Y tilde, then YT B X tilde, right? Which is for all Y. So when I'm confronted with the other player playing X tilde, y tilde is my best response, and vice versa, right, when I'm confronted with the other player. And Nash, in this very brief paper in PNS that I was mentioning before, proved that like any one of these type of games that we're going to see today has at least one Nash equilibrium that is mixed or pure strategies. Notice that like what are pure strategies in this context is just when I put all of the mass in one of these, that would be a pure strategy. Okay, so this is the definition of a Nash equilibrium. And then when we are doing evolutionary game theory, instead of having two players per se, we have a slightly different formulation in which we're thinking of strategies as populations themselves. Right? Imagine like in a rock, paper, scissors, there would be a population of rocks, a population of papers, and a population of scissors. Right? And these could be populations in the sense of like different species or different phenotypes or different behaviors for the same type of individuals or different sexes or whatever you want, right? The object of these changes depending on the focus of your research, but we have like these, that we have a certain population, we divide it into these classes that we call like the strategies. And because of that, we basically track only one set of mixed strategies, right? Because we only have one set of populations. We don't have two players at this point, right? So they play against each other, and the idea is that whatever payoff they have, they invest in reproduction, right? So imagine like when the rock wins against the scissor, it wins 1 point, and it creates another rock, right? And when the rock meets instead the paper, it loses one individual, right? And then we can think of this evolving through time. So this is like evolutionary game theory. In this context, what is important is this idea of evolutionary stable strategies, and these evolutionary stable strategies, we have another two conditions. The first one is, now we have x, because we don't have x and y anymore, right? Or you could think of this being x tilde, right? So that both players play the same thing. So we call this an evolutionary stable strategies if xt ax is greater or equal than yt ax, meaning the response of x to itself, right? So if imagine that we have two players that they have to play the same set of strategies, the same mixed strategy. So if the response of this to itself is better than any other response to itself or equal, and then there's a second condition that basically gets rid of this equal sign, and then we're saying if y is different from x, then ytax, so the payoff when this is y and this is x, is equal to xtax, implies, so when we have this equality, it implies that xtay is greater than ytay. So like when we have this kind of condition, right, that it would be equal, so here we have the equality, right? So when it's equal to play y or x against x, then x is an evolutionary stable strategy only when it plays against y better than y plays against itself. Okay, so these are a bit abstract, and that's why I like to introduce this idea of a replicator equation, right? Because then this thing will become much more tangible, like both Nash equilibrium and evolutionary stable strategies. So the idea of these replicator dynamics is that we track proportions, right? Because we're bound to move on the simplex, right, that we defined here. So we're in the space of these mixed strategies or like populations that are on a simplex that they sum to one, right? Proportion of population of each kind. And we want to track these dynamics. And in very general terms, the replicator equation is very easy to write. We could say dxi dt is xi fi minus f hat. So what is this? Now that's where the complications arise. So this we would call the fitness of phenotype or population I, right? And because we are bound to stay on a simplex, so we cannot have, for example, all populations have positive fitnesses, they would move away from 1, right? Then we have to bring them back by doing what? By subtracting the average fitness across population. Okay, so this is the most generic form of a replicator equation for this kind of matrix game that we're going to see today. You can write it a little more explicitly, thinking of dx dt is diagonal of x, and then ax, which would be a vector, and then with a slight abuse of notation, I'm going to write x dx ax, which is actually a number, but you can imagine, you subtract a constant to the vector. Okay, so this plays the role of the fitness, right? So if I win against the other player, I get like a positive number here. And this, I'm mediating. You can see this is basically a weighted sum, right? Because if this is the fitness of each player, right? So if I have fi is ax component I, right? That's what I'm saying here. What is this? This x transpose ax is the sum I and j of xi, you can write it like that, for example, xi fi. So you can see this is a weighted average of the fitnesses in which we are taking like the proportion of individuals in each class to contribute to the fitness. I see puzzled people. Questions? Where is the T? This D? Yeah. This is the diagonal. Yeah, it's exactly like we wrote before. And in fact, you should notice that this is very, 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 very similar to Lotka-Volterra dynamics, right? If I were to put like this x is my xt ax is my growth rate that are all the same, now this is like one glimpse of this thing. Is basically the cousin of Lotka-Volterra, but now we're going to see it in a little more detail. All right. Any other questions on these? Yes.
If you subtract the number from a vector?
Yeah. So these you would have to think of like one transpose, right? Like this is I just don't want to write all this stuff. These you can imagine. Like you subtract a number from a vector by subtracting the constant vector. Okay. And why do I want to introduce this? Because now this notion of Nash Equilibria and evolutionary stable strategy makes a lot more sense, at least to me. What are Nash Equilibria in this context? Are equilibria of this dynamical system. What are ESS, evolutionary stable strategies in this context? Are stable equilibria. Right? So now we have something that we can classify much more easily. Right? So if this system has an equilibrium, it's a Nash equilibrium. And then if we were to probe its stability like we did for Lotka-Volterra, we can determine whether this is accessible by evolution, right? So if I start in the neighborhood, can I go there or not? Okay? So this is the central point here. Now, one thing that is kind of different from Lotka-Volterra and leads, I think, in the literature to a lot of confusion is that when I write this equation, I have very, very, very many matrices, in fact, infinitely many matrices that would give me exactly the same dynamics. And this could give me exactly the same dynamics or exactly the same dynamics once I rescale time, which doesn't matter. What it means is that there are invariants, right? So I'm going to show you like the simpler one. There's two of them. The other one I'm going to just state. But like, we can do some algebra because it's still morning. And so what I want to show you is what if I take B is like my matrix A plus, imagine a vector of 1 that I'm going to call E, B transposed. And so this is a matrix in which we have a different constant for each column. Right? So we go in the original matrix A, and for each column we add an arbitrary constant, positive, negative, I don't care. Right? What happens to this equation? Right, then we can write this. This is like dx, so this leads to dx bx minus x transpose bx, right? And then we can expand this and say, then this must be equal to dx, and then we have a plus EB transposed x, and then we can take out this piece, and then we have x transposed a plus EB transposed x. So these I just separated these things. All right. And then what can I do? The secret here is to see when I take out this piece, right? Imagine just like, I don't want to go through the whole derivation, but when I take like d of x, e, b transposed, right? This is basically saying, you know, imagine that I would have to sum it somehow, but like, and then here I have this other term, right, that we can write also as basically d of x, a plus e, b transposed, but there's a minus in front, right, and these both would be multiplied by some vector, say of ones. These will cancel, right? So when I go through this derivation, what you find here is that we recover exactly the same dynamics, right? So this is kind of very different from Lotka-Volterra because of what? Because it means that these numbers, I cannot really interpret them as anything, right? Because I could take, I say, oh, there's a plus minus in Lotka-Volterra, then it must be some sort of consumer resource. Here I can turn that into minus minus, plus plus, or whatever I want, or plus 0, and have exactly the same dynamics. Right? So because there's infinitely many matrices that have the same dynamics, the interpretation of this coefficient gets a little trickier.
Sorry.
Yes?
This somehow makes sense to me, but I'm not seeing it in the equation. In the first line, right, d of x is proportional to x, right? So the second term should be cubic in x, not quadratic.
Sorry, I don't see that. Like this, the first term is like dx bx,
Yeah.
right? So then I say b is a plus ebt.
Right, but the second term, you lost d of x, right?
I've lost the d of x. Oh, that's true. Yeah, so let me go back and do it again, and then I'll do it better.
Yeah, because I guess I'm worried. It seems like there's a term which is quadratic in x and a term which is cubic in x. And
True, and I think I lost one piece. Anyway, I'll do this again and then I'll post it again. It's easy to change. The other invariant that I wanted to mention is that you can also multiply each column by a positive number. That has to be positive. And this would basically amount to a strange rescaling of time, where you rescale time for each species separately, but it's also invariant. So in general, whenever we have two matrices and we can write one as the other with this type of configuration, let me write just that, is if we have A2 is equal to A1 multiplied by any diagonal on the right, so that this will multiply each column, plus EB transposed, then A2 and A1 belong to the same group, like to the same class, and they would give you the same equilibria, the same stability, the same everything. They would go eventually to the same attractor. Okay. So for the remainder, I think, of this lecture today, I will focus on zero-sum games, and we're going to do like a replicator equation on zero-sum games. What does it mean to do zero-sum? It's like many games in which whoever wins gets whatever the other player is losing, right? More mathematically, like we can say zero-sum. These are zero-sum symmetric games. What we're going to look at things in which A is equal to minus A transposed, right? So that if you sum A and minus A transpose, like if you sum A and A transpose, you get a matrix of zeros. Okay, the simplest case of this that we all played is like rock, paper, and scissors, right? So in which case we have our matrix A. We have three strategies, right? Rock, paper, and scissor. Rock, paper, and scissor. And when rock meets rock, nothing happens, right? It's a tie. When rock meets paper, what happens? That rock loses, right? -1. They lose $1, say. When rock meets scissor, they win $1. And then we can go on like that. And we have here, like, of course, they have to be, whenever there's a -1, we have to have a 1 in the corresponding coefficient. Then we have -1, 0, 1 minus 1. Okay, so this is like zero sum because you can imagine that if I take the transpose, I have exactly the same matrix, but the signs are switched. So if I sum this with its transpose, I get a matrix of zeros. Yes? So now, when we have this kind of formulation, actually, you can see that the average fitness here, because it's zero sum, it's what? It's 0, right? So that makes like things even simpler, and we will see that in a second. Before I do that, like, I just want you to do some like very basic simulations of this rock, paper, scissors system, because then you get an intuition of what's going to happen, and then it's easier to do the math when you know the answer. So this is like code to integrate the replicator equation. The only thing that if you ever want to work on this stuff, there's a little problem, which is you have to keep these equations on the simplex, and because we're doing numerical integration, that is not super trivial, right? Because small errors will eventually magnify this, so you get to all speeds going to infinity or all going to 0. So just to add a little bit of numerical stability, what you can do is whenever you evaluate the function that you want to integrate, you put it back on the simplex, right? By saying like my new x is whatever it was before divided by the sum of the x's, right? If you don't do this, and especially if you use some sort of like very generous integrator like Allesina or something like that, it will go very rotten immediately. So this is just like a side note on the numerics of this. So we have our definition of the replicator equation here, which is very easy to do. And then we have, like as we've done before, like a function to plot, a function to integrate dynamics. And then we choose some initial conditions, right? And then we integrate. So here, for example, I chose as initial conditions, 0.29, 0.36, 0.24. What happens, so these are the three populations. Right? Imagine rock is, I don't know, red, paper is green, and scissor is blue. And what you can see is that they oscillate up and down, right? And they oscillate about what? About 1/3. Right? What is 1/3? It's the Nash Equilibrium, and it's actually the optimal strategy to play rock, paper, scissors. Like, there's no way to win at rock, paper, scissors, so the best you can do is to get a value of 0, which is exactly true for all these kind of games. And how do you achieve a value of 0 is if for every time you play, you just draw these at random with equal probability, the three strategies. Okay? But you can see that we're not going to this Nash Equilibrium. We're cycling around this Nash Equilibrium. And then let's try the same thing, but now that we know that we have 1/3 would be the Nash equilibrium, what happens to the system if we start it there? So instead of starting at these random initial conditions, now I start the equation at 1/3 each. And what you can see is that now they stay there, right? Which tells you this is really an equilibrium, right? So if I start the system at an equilibrium, it will stay there forever unless perturbed. And then if I start it very, very close to 1/3, then I will have small oscillation. Okay, and this is what it's done, for example, here, where I started like very, very close to 1/3 each, and you can see that the oscillations are very small. Okay, so this should remind you of something. What does it remind you of? Predator-prey dynamics, and especially the original papers by Lotka-Volterra that had what? Like this equilibrium that is in the middle, that is stable or not stable? Neutrally stable, right? So like this idea that is a fact like what got like the interest of Lotka-Volterra, right? Of this type of phase plane where we have this equilibrium and then we have some sort of orbits, right, that goes counterclockwise in this system between predators and prey. Right, so this is really reminiscent of that, and as we will see later, this is exactly what's going on. All right, now I told you several times already that the Lotka-Volterra and the replicator equations are related, right? They're cousins. And so now I want just to make this a little more explicit. And what I want to say is that for any n-species generalized Lotka-Volterra model, there is an equivalent replicator equation that has n plus 1 phenotypes or whatever you want, so it goes up of one dimension. And there's a matrix, like of this kind that we were drawing, that has all zeros in the rows, in the last row. And how do you achieve this matrix, right? So imagine that I have my matrix A is my matrix of the generalized Lotka-Volterra model. And now, and this is n times n. And then I have my R's, right? This is a vector of n. And now I want to build my n plus 1 times n plus 1 matrix for the replicator equation. Okay, a way to do this that abides by these rules that I was saying is like you take the n plus 1 matrix, and then you put A here, right? So the first n rows and columns, you put A. You put R here, and then all of these are zeros. Okay? So these generalized Lotka-Volterra model and these replicator equations are equivalent in the sense of if this is stable, this is stable. If this goes to some proportion, this will go, once you scale like the proportions, to the same type, etc., etc. If this is a limit cycle, this is a limit cycle. These type of things. Okay, so this is very convenient because sometimes it's easier to work with the replicator equation, and sometimes it's easier to work with Lotka-Volterra. So depending on which one is your focus, you can switch freely from one to the other. So how to show you how this is done, what we're going to do is like run Lotka-Volterra, then build this matrix, B here, then run the replicator equation, and then show how can you go back to Lotka-Volterra. Then we're going to do the converse. So these are just the functions that we've seen yesterday and the day before to integrate Lotka-Volterra. And then I just take a simple system, with 3 species. This is my matrix of coefficients, and this is my initial conditions. And I integrate this system. Okay, so these 3 species coexist. Like species 2 and species 3 are about the same, and species 1 is higher. And you can see this goes to some sort of stable equilibrium. Okay, so now what I'm going to do is exactly build the matrix B in this way, right? So you can see that I take an empty 4x4 matrix, and I put in the first 3 rows, 3 columns, the matrix A. In the 4th column, I put the vector of growth rates R, and the rest are 0 because I started them at 0. And so we should be able to see this matrix. And so this is how my matrix looks. It's over here in the board, where you can see that the last row is all zeros. And now we have dynamics for a 4 differential equation system, right, on the simplex, this replicator equation. But what you can see is that there's one species, species 1, that goes up, species 2 and 3 that before they were together are together again. And now we have this fake species, species 4, right, or population 4, that is the purple that goes to some place. Okay, but how do we recover the information on the Lotka-Volterra once we went through the replicator equation? All right, so first let's look at the equilibrium of the Lotka-Volterra model. So if I just go into my dynamics and take the last time step, you see that it went to an equilibrium, and this is my equilibrium, right? So let's write it somewhere so that we remember. We have 1.32 for species 1, and then let's write only 2 because then the third this is 0.538 for species 2. Okay? Now, to recover, we can do the same and look at the equilibrium for the generalized for the replicator equation, right? But now we have 4 things, and these 4 things are bound to sum to 1 because they have to be on the simplex. So how do I recover these numbers from that? All you need to do is to take these densities and divide by the density of the extra species. In this case, the 4th species, right? The one that has the zeros here. And then we can recover our equilibrium. So these are like the 4 species equilibrium. Now I take the same thing, and you can see I divide by the density of the last species. And what do I get? 1.32, 0.538, 0.521, right? So this is exactly the same as the Lotka-Volterra. Now, this is like showing you that there's a way to recover the same equilibrium, but in fact, everything is the same. Up to rescaling of time, these two equations are doing exactly the same thing. All right. Now, because of these equivalence that I was talking about before, I can take any replicator equation and then add a constant such that the last rows are all zeros, right? Because I can add a constant to each column, right? So I choose to add the constant whatever is on the last row with a minus in front, and now I recover a structure that looks exactly like this. Does this mean that then the Lotka-Volterra defined by these vectors and these A will have the same dynamics? Yes, it does. Right? And in fact, I could choose even like to be the R's are here and A is there, or R is whatever you want. These will all be equivalent to the same replicator equation that we had before. Okay? So this is why this is a bit more confusing to interpret this parameter. Are these the growth rates or are the next column the growth rates? You choose. Like, it doesn't matter. All of these will give you the same exact map in the same replicator equation. Is this clear or not clear? If it's not clear, ask questions. But now I want to show you, like, while we wait, what can we do is to take this rock, paper, and scissor, turn it into a Lotka-Volterra, and then integrate the Lotka-Volterra. Then now we'll have only two species, right? Because we started with 3, we have to go back to 2. So like this is my matrix, right? So imagine that I have my matrix here, and now I decide for the first column I add 1, right? So that the last row is 0. So I have 1, 2, 0. The second I subtract 1, so that I get 0 here, right? So I get -2, -1, 0. And the third column, I leave it like that because it's already 0. What is this? Who knows? But like what we could think is like these, for example, we could take these to be the matrix of interactions, right? And these to be the growth rates. This would be a predator-prey system of some kind, Lotka-Volterra, right? But I can also take these to be the matrix, and that's what I'm doing there, and these to be the growth rate. What is this? Who knows? It's difficult to interpret something with a positive diagonal associated with a positive growth rate. I don't know how to interpret that. And these two are both mapping in the same replicator equation. Right? So if I do like one of these things, for example, now I have this formulation where I take these to be the growth rates, these to be the interaction metrics, and I integrate. What do I have? I have cycles, right? Because I had cycles in rock, paper, scissors. These are neutral cycles, and they will go about what? Right? They should be cycling around 1. Right? Exactly because they have to have the same density. Right? So it's difficult to recognize which system maps into which, but this thing is very convenient, right? Because if I have some better choice of rows or columns, I can do that. Solve the Lotka-Volterra for that. For example, imagine that I could get something with a constant column somewhere. That's great, because then I will reduce the problem to n-1, and then I could reduce it to n-2 by doing this back again. Okay, so this, I think, it's an underexploited connection between Lotka-Volterra and the replicator equation. So this rock, paper, scissor is a simple case of what we call a tournament game, right? And because I think we have time, what is a tournament game? Like we have some strategies, like imagine in this case we had 3, right? Rock, paper, and scissor. Paper and scissor. And then for each pair of these, we draw an arrow from, say, the loser to the winner. Right? So for example, rock loses to paper, scissor loses to rock, and paper loses to scissor. And you can see that like when we have these cycles, right, in like rock, paper, scissor, what we have is what we would call some sort of intransitive competition or things like that. Now, some tournament games are not very interesting, like because, for example, if I have another strategy here that loses to all of them, will we ever play W? No, right? Because why should you play W? You're about to lose with probability 100%. So that's not interesting. So you can imagine that if I had like this where my species competing for something, W would go extinct for sure, right? And it would go extinct very quickly. But what can we do here is like to build larger games if we wanted, right? I don't know, there's like this famous case of the rock, papers, scissor, lizards, and Spock, right? And all these games, how you have to build them, it's very simple. You take any node, say rock. This rock has to lose to half of the other players and win against half of the other players, right? And then you do this in cycle, and you get a new game. That it's exactly like rock, paper, scissors, but it's more boring, right? Because now you have to memorize 5 strategies, and then at some point you will run out of like gestures that you can do, and this is what it is. Now we could complicate these games a little. Instead of saying like there's 100% probability the rock will win against scissor, we could say there's some other probability, right? And so now we have probability that rock wins against scissor, and probability say that scissor wins against rock. So these we are still in the zero-sum realm, but we have a slightly more general case, and these are called hyper-tournaments in game theory. Right? And so what we have is basically still that like we have a matrix of payoffs that is skew symmetric, right? That's like, and we can generate this matrix of payoff from these probabilities of winning and losing, and we will see that in a second. What I wanted just to say is, like, as I said before, that when we have these zero-sum games of this kind, then if you sum the average fitness, it has to be 0, right? Because if somebody wins, somebody else has to lose, so they must cancel each other. And as such, this replicator equation simplifies a lot, right? It becomes just d of x, ax. And then this means that either the part in d of x is 0 at an equilibrium, or ax is 0 at an equilibrium. But if ax is 0, meaning all the strategies are present, and they're at an equilibrium, what I'm saying is ax is equal to 0, which should remind you of something that you've learned in linear algebra. What is this? It's an eigenvector, right, associated with the eigenvalue 0. So if all strategies persist, you can find the optimal strategy by looking at this eigenvector. If not all strategies persist, and then it's a little more tricky, right? Because you have to find which one should I zero first. And then for the subset, I can find it with the eigenvector. Or what you can do is, that's what we've been doing for a while, there's this technique to solve this type of games that is called linear programming. So you can write this as a linear program. So it's like maximize something, in this case, the value of the game under some constraint. In this case, like that all these things must sum to 1. And then you can do that. All right. So for the remainder, I want just to talk about how can we introduce this replicator equation to study ecological dynamics. So are there situations in which we can think that the replicator equation would map into an ecological model per se, without having to massage it from generalized Lotka-Volterra model into the replicator equation? In the case I want to think of, which I think it's a simple one to think of, is, for example, a tropical rainforest. So in a tropical rainforest, we have a certain number of trees, right? And these are tightly packed. Like if you think like from the canopy, if you take an aerial picture, there's no hole, right, in this canopy. And this we will take to be, there's a fixed number of trees. Now, is this really fixed? Not really, but it's fixed enough that we don't really care whether it's fixed or not, right? So it fluctuates much, fluctuations are small. So we have our trees. And this is somewhat of a magical forest that we're going to look at, right? So we have our trees, and these trees maybe are of different species, right? And whatever other species that we have. And there's a fixed number of them. And then every so often a tree dies, right? So when the tree dies, what happens? That there's a hole in this canopy that then can be filled. And because this is like, as I said, a magical forest, there are like these magical creatures that look after the forest, and what they do is that they have like, they go and gather all the seeds from all the trees, and then they pick 2 seeds at random, and they just plant them, right, to fill the gap such that the forest can restore itself, right? So here we will have, for example, two seeds, this one and this one competing, and one of the two will fill the gap. And then we go back to the filled forest, and then something else dies. And then we pick these two seeds, right, at random with proportional to what are the species around, and then we fill the gap, and then we repeat this process over and over. This is like an example of this, but you could also think of, I don't know, mussel bed, right, where if you see like mussel beds, there's no space for any more mussels, right? So the only thing that happens is that every so often something comes by, a big wave or something, it detaches a piece, and now there's bare rock that can be colonized again, and eventually will be colonized again. And you could imagine that this will be proportional to the densities of these species of mussels in the water column. How many propagules will they get there? Okay, so now what we need to do is to say, if we have two species, I and J, what is the probability that I wins when competing for closing this gap, and what is the probability that they lose? And we call this Hij is the probability that I wins against J when competing, and then Hij is the probability that J wins when competing, and they must sum to 1, because somebody has to win eventually, right? There's only two seeds there, so they have to win. Okay? So this is a model that actually was studied by Jacopo and myself and other people in 2017. You find the reference there. And so you can write really like the process of I pick the seed with this probability, this is the probability, this wins, this is the probability, this loses. And what you end up with is like a differential equation that looks like that, which is fairly straightforward. Like -1 would be the probability that tree, like the rate at which trees, species I die, right? And we take it to be the same for all the species. And then these you can think is like the probability of getting a seed of species I and J, right, which will happen with probability with some rate that is proportional to xi and xj, and that's why they multiply. And then because I'm looking at I want to know what is the probability I wins, right, Hij. And then there's a 2, because when I sample two seeds, I could pick I and J or J and I, but it's the same, right? It's the same pair, and that's why there's the 2. And then what you can do is to massage this thing, because you can always think of 1 as being the sum of all the xi, right? So if I do that, then I can take this sum also over these parts here. And then I can always think of Hij as 1 minus Hji. And so through this massaging, we get like the replicator equations that we've seen before, but where we have like our matrix A that is just like H minus H transposed. And this the payoff matrix would be H minus H transpose. And you can do this for rock, paper, scissors, and you would find exactly the same that we've seen before. So if I have 3 species and they happen to be rock, paper, and scissor, the dynamics would be exactly what we've seen before. Now, rock, paper, scissor is also interesting because can we have 2 strategies coexisting with each other? So imagine that now we can only play rock and paper. Right? Then we would always play paper. Because if you play rock, you lose, so then we cannot have 2 strategies. We can have either 1 or 3. Okay, it turns out that this holds much more generally than that. And this is like something that I found out like in some old papers on game theory in 1995, etc. And I put in this Allesina and Levin. This is like a paper introducing this type of tournament games and this type of models. And when I found out this fact that I could not get an even number of species to coexist, I was kind of weirded out a bit, right? So I was like, this is so not going to fly with ecologists, because no one knows really how many species are on Earth. We don't know, about 9 million. But is it an even or odd number? No one can answer this, right? So I don't have good evidence against this. But so this turns out to be a very strong feature of all these type of games. And so what we would like to do is what we did like yesterday for the random zoo, right? So if I put like a bunch of random species together, and then I run the dynamics, how many species will I get at the end, right? So if I start with n, how many do I get back? Exactly the same problem that we did yesterday with this generalized Lotka-Volterra model. And as we will see, the answer is also very similar. So now we have to define what do we mean by random matrix. And so what I mean is just like we take Hij to be a number between 0 and 1 at random, uniformly distributed, and then we pick Hji to be 1 minus that. And so this is what this part of the code does. Or similarly, like we can say, take random numbers and then take the symmetric part of that. On the diagonal, we should get 1/2, right? Because if you're playing against yourself, one of you will win, but which one of you will win is at random, right? So that's what will happen. And then, as we did yesterday, instead of like wasting electricity, like I'm an ecologist, so I really care about conserving energy. Instead of like integrating differential equations on this computer, we're just going to find the optimal strategy, meaning like the final solution of this game by doing linear programming, right, which should go much faster. So this is what this code does. Or you could integrate the dynamics if you want to waste electricity. Okay? And now what we're going to do is just like take a certain number of strategies or / species, right, in this case, 10. And then what we're going to do is just like to choose a number of simulations like we did yesterday. We do 5,000. And then for each one of these, we just build a random matrix H. We find how many species are coexisting, and at the end, we tally, and we show like this histogram. And so this is the result, which looks fairly similar to what we had yesterday, with the exception that we cannot have an even number of species, right? So we have 1, 3, 5, 7, and 9, but we cannot have any even number of species. Now, this might seem very strange. It makes a lot of sense in this, if we're thinking of building like the boring rock, paper, scissors with however many strategies you have, right? And I told you like the recipe to impress your friends by inventing a new rock, paper, scissors with 23 strategies is what? Like you take all these things, right? Imagine that we have 5 or 7. Then you choose a focal node and say this one loses against half, wins against half. And then I repeat cyclically. But this can only happen when I have an odd number of strategies. Otherwise, how can I divide the rest in half? Right? And so this is like an intuitive explanation for this type of thing. But turns out that this is basically like the binomial distribution, but we distribute the mass only on the odd numbers. Right? So on average, we still get a half of the species coexisting, and we get a variance of 1/4 of the species coexisting, and this is the density function, right? So it's n choose k 2 to the 1 minus n. So instead of having 1 over 2 to the n, we have n minus 1 there. And then when k is odd, and then we make up for this other part of the distribution by saying it's 0 when k is even. Jakob, how are we doing on timing? Yeah, let's have the little break, and then we wrap this up.
And then we come back. So 5 minutes.
5 minutes, and then we come back. Coffee break without coffee. That's
Sì, sì, sto facendo così.
Let's start again. So, I think it's a good moment to ask questions
Yeah, it's a
if
good
you
moment
have
to ask questions.
any.
If there are questions. Okay, there are no questions. So you remember yesterday or the day before that we wrote Lyapunov functions to show how marvelous, like this system goes always to the same place, so we can prove global stability. Turns out we can write a Lyapunov function for this system as well. But should it be globally stable? We've seen, like in the rock, paper, scissor, that what happens? Right, that it oscillates forever, right? So it cannot be globally stable. Thank you very much. And in fact, if you go through this motion of like computing, this is the Lyapunov function that, I don't know who found this, but like you find it in all the textbooks. And you go through like this whole derivation for this type of games that we're analyzing, what you end up with is a 0. Right? So this function is 0 everywhere, which means what? That we have some sort of constant of motion, right, in the system. That if we started like at some point, this quantity will be preserved because like it does not change in time. And in fact, like what we expect generically is this thing to just cycle neutrally, so that depending on the initial conditions, you know, like what, and depending on the matrix H, the generic behavior is some of these things will just die immediately because they're like strategies that lose to more strategies than they win to, or they lose to the base strategies more than they should. And so they go extinct very quickly, and the rest of them will cycle neutrally for forever. Okay? So let's try just this with 5 species. And so you can see this kind of cycling going on for forever. Why is this bad for an ecological model, right? This is a very bad ecological model for at least 2 reasons, one of which is fairly obvious, like that if I start very far from my optimal strategy, right, from the solution of this Nash equilibrium, then I will have very large oscillations. And now, if we're not in the magical forest where there's an infinite number of trees, what happens is that due to stochasticity, some of these will go extinct. And imagine that you have these 3 rock, paper, scissors species in the magical forest, and one of them goes extinct. What happens then? Another one will go extinct immediately after, and we end up with a single species. And in fact, this is the generic behavior that we expect for all these models, is that, you know, as soon as something goes wrong, they will start like unraveling, and eventually we will end up with like a single species. Even worse, that it's not easy to see here, but you remember that they put in some sort of constant death rate for this system. Right? Basically, there's a constant death rate for all the trees. If I perturb this one slightly, right, instead of having all of them exactly identically, have one is like slightly better than the other ones, what happens is that these cycles, instead of being neutral, they start amplifying, and then eventually the system goes back to one species. So this is bad for multiple reasons. These 2, I think, stand out as being particularly bad for ecological dynamics. Yes, question?
This is because you have a zero-sum game, right? For
Right.
this particular case.
Yes.
So if you allow the game to be, if you like to hop those, you can have a mixed strategy where both survive, right?
Right. But like if we're tracking proportion of anything, it has to be to some. Oh, yes. So this was like, the question was, is this due to zero-sumness of this game? Yes and no, like in the sense that for anything where we track relative abundances, imagine yesterday we were looking at bacteria in the gut, right? And we were looking at the relative abundance, it must sum to 1, which means that if something goes up in relative abundance, something else has to give, right? Which basically makes it a skew-symmetric matrix.
Yeah, but the payoffs don't sum to 0, right?
Yeah, but that does not matter. Like if we're looking at, let's write this for the replicator equation. Like the question is, but they pay off, they don't sum to 0. So I showed you like this formulation of saying dxi dt is xi times fi minus f hat, right? Where f hat is the sum over, say, j of xj fj, right? So if I do this, let's write xi. Let me think, because I've tried to do this derivation on the fly. Minus a of j of xj fj. Now can I get this? So what did I want to do?
So you are trying to prove that the x sum to 1? That's clear. I mean,
no, not that the x sum to 1. That this, I can always write it as a diagonal of x, fx, where this f is a matrix, fij is f of I minus f of j. And so this is a skew-symmetric matrix. Right? It's exactly like in the other game. And this is for a generic game. Like this doesn't even need to be a matrix game. Does this make sense?
I'm not sure. For instance, take the hawk-dove game, right?
Yes.
So there is a strategy where you have a fraction of hawks, a fraction of doves. It's a stable strategy. And you don't have this cycling, you don't have this problem.
Oh yeah, I'm not saying that all the matrix game will have cycles. I'm just saying that all these things that we're doing in this replicator equation, they basically have some sort of zero sumness to them, right? Because of this fact, right? Because if something has to go up, something else has to come down eventually, right? Because we're tracking the relative abundances. So like I feel again that this is an interesting. Actually, this will be even more interesting after this discussion. Because I told you that we're in this magical forest, right? So these magical creatures decide to put 2 seeds. Every time there's a gap, they put 2 seeds. But what if the magical creatures decided to put 3 seeds, or 4 seeds, or 5 seeds, or 7 seeds, or whatever other number of seeds? And now we have to picture this as some sort of like picture in our head. And the way we're going to do this, if I find my chalk, is that we're going to do some sort of like competition, right? So we have like our 3 seedlings, seedling A, seedling B, let's make it of a different shape, and seedling C. And so these arrive like the magical creatures planted, but 2 of them are closer to each other, right? So these 2 are closer to each other. So first, they will sort it out themselves, right? So one of them will win this competition in pairs, and then the winner will take on the 3rd challenger, okay? And so can we write equations exactly as we did before for this case where we have 3 seeds? And then if we have n seeds, we can do the same, right? We first compete to the 2 closest, and then these with the 3rd closest, like and then we can go on like that. And so this is basically saying, can we play a game like rock, paper, scissors with more than 2 players, right? That's what we're asking, right? So can we massage this into the replicator equation? But instead of having 2 players playing at each point in time, we have 3. So, like, because I want to send you home with like very important information. I showed you how to build a rock, paper, scissors that is very boring with n strategies where n is odd. Now I'm going to show you another thing that is very important for like your well-being, which is how do you play rock, paper, scissors with 3 people, right? So, such that it makes sense, right? Such that it abides by the rule that we would think for rock, paper, scissors with 2 people. So imagine like as exactly in rock, paper, scissors, we have 3 people and they just like do their thing and then they throw their strategy down. Now, if everybody has the same strategy, what should be their payoff? 0, right? Exactly as you would for 2 players. Now, more interesting, if all of them have 3 strategies that are different, right? So if one plays rock, one plays paper, one plays scissors, what should happen there? Right? So you could imagine this of like trading dollars. I give $1 to the person I lose to. This person gives $1 to the person he loses to or she lost to. And this person gives it back to me, right? Because I also won against them. So we have, again, 0, right? So the only interesting case where money changes hands is when 2 players play one strategy and 1 player plays another strategy, right? In which case, if there's 1 winner and 2 losers, they both pay $1, this person gets $2. If there's 2 winners and 1 loser, this person plays $1 and they get 50 cents each. Okay? Do you agree with me that this is the way to play rock, paper, scissors with 3 people? Turns out there's an International Society for Rock, Paper, Scissors where they have a section that writes the rules for playing rock, paper, scissors with 3 people. It is exactly these rules. Okay? Turns out that if we were to do this, what we could do is to write the rock, paper, scissors replicator dynamics with 3 players, right? So what we would like to do is to write a replicator equation, but instead of having a matrix, we have a slightly more complicated object that would be a 3-dimensional matrix or a tensor, right? Because now we have to account for all the possible triplets of players that we have. And so what we would get is like dxi dt is xi, and then we sum over j and k, ai, j, k, which is like this tensor, right, this 3-dimensional matrix, xj and xk. So how would this, like, let's say, this we can look in slices, right? So let's look at the rock slice of this tensor, which would be a matrix that goes like rock, paper, and scissor, rock, paper, and scissor. And here we report, for example, the payoff for player rock, right? So if player rock, 1 plays rock, 2 plays rock, 3 plays rock, what happens? 0. If player 1 plays rock, player 2 plays rock, and player 3 plays paper, what happens to player 1? Right, they lose $1. And then if player 1 plays rock, player 2 plays rock, and player 3 plays scissor, we have 1 loser, right? But we have 2 winners, so they win 1/2. And I don't know, let's fill this in, like, but then this would be exactly the same as that, right? Because it's just like who is player 2, who's player 3, it's pointless. And then if there's 2 papers, what I do is I also lose only $1. I have only $1 to lose, so I cannot lose 2, even though there's two winners. But if there are 2 losers here, I win $2, right? And then I complete this by taking the symmetry. And then I'm missing 1 number here. 1/2, 1/2. Well, these are the cases in which we have like rock, paper, scissors, right? All the strategies are played 0. Okay? So you do this, and then like the same slice for like the paper and for the scissor would look the same, but like with the rows and columns scrambled in some meaningful way. And so then we could play this replicator equation with 3 players at a time. Yes? Aren't you impressed that now you can go home and play rock, paper, scissors with 3 people? And in fact, you can play any of these games with 3 people. It gets a little more tricky, like, to decide this kind of payoff, but there is like a rule that you can derive, Jacopo and his collaborators derived, like in this paper, where you can just start from this matrix of probability of winning and losing, and you can get to this payoff matrix. Okay. What happens to the dynamics in this case? Right, so before we had these kind of cycles that we didn't really like very much because of all the problems that I told you. And so now what we're going to do is just like have the same type of differential equation, right, that only has this tensor. And we have a way to build a tensor. And so now we can build a tensor and then just integrate the dynamics of whatever system at random. And look what happens. So going from 2 to 3 players playing at a time, amazingly enough, does not change the location of the Nash equilibrium. It's exactly the same as before because we're choosing this very natural way of extending this, right? Exactly as I told you, like we play rock, paper, scissors with 3 people, but we want to have the most natural extension, right, that makes sense with the rules. But this changes the dynamics dramatically. Instead of having a neutral cycling, now we have a globally stable equilibria in the simplex, right? So this Nash equilibrium that before was not an ESS when we play with 2 players becomes an ESS when we play with 3 players. And then somebody should raise their hand and say, hey, Stefano, what happens if I play with 4 or with 5 or with 6 or with 7? And I can tell you, nothing much. Like it goes to the same equilibrium, but just faster. Right, so you can write this thing. It gets a little tedious, but for 25 players, you could write that. Right there. Sorry? Oh, this is like a random system with 5 species. Let me show you also rock, paper, scissors so that you can see better. So this, I think, is like the rock, paper, scissors. So if I just take the same as before, and now I do rock, paper, scissor, you have this beautiful convergence to this equilibrium by cycling. Okay? So this is one nice feature that we go from some sort of neutral stability to global stability in this Nash equilibrium, so it becomes an ESS. The other nice feature is that I told you that this was very unrobust perturbations of the parameters before, right? So that if I change the death rates of these of a little bit, it would burst into flames and we would end up with a single species. This turns out also to remedy to this problem, right? So that this is also now robust. So it's a kind of a surprising result. And it begs the question, for which I have no answer right now, of how do I solve the Lotka-Volterra with 3 species interacting at a time, which is what we would call a higher order interaction. Okay? So I think we have time for questions. I would leave it at this, but we can get into more details in the questions. Thank you.
Stefano, thank you for the lecture. Since you already answered the question of what about the generalized Lotka-Volterra with higher order interactions, I'd like to ask as well, like, can you recover? You showed that you can recover the Lotka-Volterra system from this kind of game dynamics, but can you recover the strategies dynamics from the Lotka-Volterra, because you like lose an equation or something?
You cannot. I don't think you can. No, because these extra species that you're putting in basically plays the role of the environment, right? Imagine that how much is the environment losing to the population, right? Because when the populations are growing, the environment keeps losing, something. And then it has to equilibrate such that they match the input to the environment, right? That's the idea of these extra species, is like the external environment that is playing this thing. So I don't see how would you go back.
And have you looked at some kind of reasoning close to this one? Because I don't think it's in relation to the Lotka-Volterra with higher order. Like I assume it is much harder to do the partitioning of a tensor. And
exactly. That's it's a little more complicated. What we would like to do is to find first the class of invariants, right, that we can have, right? Because if it turns out, for example, this tensor, you can imagine that only the symmetric part matters, the non-symmetric part goes away, right? Because then I'm summing over player 2 and 3, and then player 3 and 2, so this will go away, right? So that's, for example, something that I can always do. I can add whatever, and if they have the same symmetric part, they will be the same dynamics. But are there more general relationship of equivalence like the one that I showed you? If that's the case, then you could start thinking. But even there, you see, there's 3 Lotka-Volterras here, right? And I can choose whatever I want, and they both, all of them map into the same replicator equation. So I think it's getting somewhere, but it's not where I would like it to be. That's my...
Thank you for the lecture. I find it very surprising, almost everything that was talked about here. But maybe the most surprising thing, and why maybe intuitively should adding higher order interactions stabilize the equilibria, right? That's so weird.
Yes. I have a somewhat head-wavy explanation. I chalk it up to separation of time scales, right? So what happens is that we have this replicator equation, and this replicator equation for a zero-sum game sits at a corner of some parameter space. And this is the weird corner of this parameter space, right? In which we have these neutral oscillations. If you kick this model in any direction, it falls back into global stability. Just to give you another example, there's a paper that I'm not citing here, but it's a paper that came out in 2019, I think, last year, in Ecology Letters with Dan Maynard. I can send you the reference, where we do the same thing, but instead of having populations of all rocks, imagine that rocks has 15 phenotypes of rocks. And Scissor has 7 phenotypes of rocks, which are all rocks or all scissors, but they're marginally different, right? As you would, like you have bacteria of the same species, or the same bacteria, they're not, right? So there's variation. So if you just add variation to this thing, you recover global stability. I have another model that I was never able to show how does it work because I cannot do the math, in which you imagine like that when you colonize this empty patch, it depends on who was there. Like there's some sort of memory of who was there. Again, then I have all these simulations because I cannot do the math. You recover global stability. So this is like one general statement I want to make is that this was like seen and discarded immediately because of all this quirky behavior of having like a neutral cycling. But if you just perturb the structure in any way that is reasonable, it will change the dynamics completely. So in that sense, I'm not super, right now that I have better understanding. The first time I saw this, I was also surprised. I fell off my unicorn, as I say, you know, like when I saw this thing. You know, but now with hindsight, I'm more like confident that this is just because this is sitting really at the corner of a much more general, like stabilized system. Now, for what concerns like the higher order interactions, what you could think is like that when we're doing this type of game, right, where we have 3 players, as I showed you here, we're basically doing 2 moves in one, right? So we have like that we've decoupled the death rates, like that they have a time scale, from like this competition, right? Before they were exactly on the same time scale, right? That we have a filling of the gap takes basically the same amount of time as filling the gap. The competition for filling this gap. And here we're doing 2 steps at a time, right? So instead of doing 1 competition bout in the time it takes to die, we do 2. And then we could do 3, and then we could do 4, and then we could do infinitely many. Right? So what we're doing is separating these time scales, which also typically has some sort of stabilizing effect. But maybe Jacopo has a better answer. You have the microphone. If you want to have a better answer, you can.
Yeah, couldn't you also, about this thing here, couldn't you also interpret a system with many players like a kind of a mean field, like you are averaging over all this, if you, instead of having only 3, you said, okay, I can make this with 10 or 20 or whatever, this is kind of a mean field, and then you're always just filling the mean field, and then you quickly go to the fixed point or something like that.
That I've never really considered. It's a good question. Like you're saying, if I keep adding, these are basically, say, people that are my neighbors or something like that, right? So before I had only 1 neighbor, and now I have 2. And if I go like full blown, then I have very many. So you could think very easily of a case in which we have infinitely many of these, right? And that's actually easy to do, right? It's just like numerically, it's a bit tricky, but like mathematically, what you would do is just like now you have a probability, right? All you need to do is, what is the probability that I sample these 2 types of seeds, and this one wins? And that would be basically the stationary state of a Markov chain, right? That you can define by saying these metrics of payoffs, like their densities, right? So that we would be doing infinitely many seeds at one. That should put an upper limit on how fast these dynamics can go, right? Because if we believe that when I put 4 or 5, it does accelerate, that's what will happen.
Yeah, because I just played a funny thing, like it says, hey, we can go home and play with 3 people, but then I thought, okay, maybe we played with everyone in the room, right?
Right.
And then, but probably almost everyone would get very close to 0 payoff, because it's just
exactly.
just
Eventually,
the
they
mean.
would
Yeah.
get very close to 0. That's very true. Yeah. Do you have a better answer?
No, I mean, but the point is that these work even in the case where you have like a very large number of strategies. So you have like a rock, paper, scissors, lizard, Spock, and whatever other characters you can put it. And then you have 3 players, right? So it's not, I don't think it's an argument of like sort of central limit theorem kind of thing, right, where you average out. Because if you have 3 players in a game with like 100,000 strategies, 100 strategies and 1, you still have the same thing. So, yeah. Yeah, we have time for one more question.
In a way, can't you, if you have, like on the right-hand side, you have squared, x squared, second power,
Right.
third power, you sort of rename them, put them on the left-hand side, and increase the number, and then make it all look like linear.
This is a fantastic point. So it's something that I was tempted to put in the notes on the first day, but then I didn't because I didn't have time and it already went over time. If you have if you have any polynomial ODE, you can do the exact same trick of saying, I take xi, xj, and I call it yij. And then I take xi, xk, I call it yik, right? So now I have more variables, right? The number of variables increases dramatically, but you can always massage these such that it becomes generalized Lotka-Volterra model. You could do the similar trick here, right? The problem is what? These now differential equations, besides the fact that we're working in a high-dimensional space, sits on what? On some sort of manifold that abides by all the rules that we put in, right? So when I look at yik, it better be like the product of xi, xk at the same time, right? Because otherwise, what am I doing? And so this is kind of interesting because if you start on this kind of manifold, it should stay there, the dynamics, because the dynamics have to be exactly the same. I just need a change of variable. But then what can we do mathematically with this? I'm not so sure. I'm trying to torture the people in my lab to do this calculation for me, especially people that are more familiar with topology, because it starts getting a little bit of a strange object. But I think that something could be done in that way, right? And it's exactly the same spirit, right? That we just do change of variables. We increase the number of variables, but now we have simpler equations. All right. Thank you very much.
Yes. So we'll come back at... We'll come back at 10 past 11.